When we talk about gravitational force, it's the force of attraction between two bodies, correct? Now, gravitational force and gravity are not the same. Gravitational force is the force of attraction between any two bodies. Okay, now when we talk about gravity, we are specifying only for Earth. That is, the force of attraction towards the Earth is called as gravity. Fine. Gravitational force is more like a general definition, the force of attraction. Gravity is only for Earth. Fine. So we have gravity and acceleration due to gravity. See, acceleration due to gravity, the name itself suggests acceleration. What do you mean by that? The change in velocity over time. So as the body falls towards the Earth, so the speed of that object keeps on increasing. Fine. It keeps on increasing, meaning the body is accelerated. So the body gains acceleration because of the pull from the Earth, which is gravity. Alright. Now, the acceleration due to gravity, it has a value. This is 9.8 meter per second square. Okay. Now, this is the value. Now, one thing, acceleration due to gravity, what we are looking at here, it reaches a constant, that is 9.8 meter per second square. Like if I leave an object, let's say from a top of a building, it takes a certain amount of time to reach that 9.8 meter per second square. After that, it's constant. Okay. Now, we'll try to find a relation between this acceleration due to gravity and gravitational constant. Now, for this, we use Newton's second law of motion. See, Newton's second law of motion, it's given by F is equal to m into a, correct? Now, here in place of acceleration, we have acceleration due to gravity. So, we have F is equal to m into g. This is first equation. Now, the universal law of gravitation, that is the Newton's law of gravitation, is given by F is equal to g m1 m2 by r square. Now, here we are considering only with respect to Earth, correct? So, we'll write this as F is equal to g me into m divided by r square. Okay. Now, we can equate these two. But before equating, remember, to get acceleration due to gravity, I need to drop an object from certain height, correct? Not from the ground. So, instead of r, we need to write it as r plus h, because the radius of Earth plus the height, some height. So, the Newton's law of gravitation, that formula changes. We get F is equal to g me into m divided by re plus h whole square. So, this becomes the law of gravitation. Now, this is the force. Now, according to Newton's second law, we have F equals to mg. Now, when I equate these two, I get mg is equal to g me into m by re plus h whole square. And then now m and m cancels. We get g is equal to g me divided by re plus h whole square, right? Now, the radius of Earth is 6,400 kilometers. The height of any object, if you consider, it's going to be negligible compared to the size of Earth. The size of Earth meaning the radius of Earth, right? So, re plus h can almost be considered to be re itself, correct? The radius of Earth. So, we get g is equal to g me divided by re square. So, this becomes the acceleration due to gravity formula. Now, if you carefully look at the formula, will the mass of the object count here? No, because there is no m, right? You just have g, gravitational constant, me, mass of Earth, re, radius of Earth, and all three are constants, correct? This is why we say acceleration due to gravity for Earth is constant, which is 9.8 meter per second square. Now, to do this, actually lots of people have done experiments on this. The first person who did this was Galileo. He dropped two balls from the top of Pisa Tower. Fine. So, both of them, they reached the ground at the same time. So, then he said that, so gravity does not differentiate between two masses, it just falls at the same time. Then, Newton also did the same experiment. What Newton did was in a vacuum glass tube, he dropped a coin and a feather. Both coin and feather, they touched the ground at the same time. So what he told was, irrespective of what mass we have, the acceleration due to gravity is always constant. Okay, so this is a very famous experiment, the coin and feather experiment. So whatever value we have for acceleration due to gravity, remember it is directly dependent on the mass of the earth and inversely proportional to square of the distance of the radius, right? So here remember, for different planets acceleration due to gravity will change because the mass will change and radius will change, correct? So this is the reason the acceleration due to gravity is constant for a particular object. Like Earth, if you take, it's 9.8 meter per second square. If you take Sun, it is 216 meter per second square. Something like this. It will change from object to object.